Hi everyone, thank you for joining today's seminar. Today we have two speakers. First speaker is Tongtong Li. She is a PhD student from University of Pittsburgh, Pennsylvania. Her topic today is a new fully mixed formulation for the Stokes-Biot model. And our next speaker is Anna Helen Sisk. She is from University of Tennessee, Knoxville, Tennessee. Her topic is epidemic models of violence and network models of food deserts. The context is looking at community issues through the lens of mathematical modeling. So first, I would like Tongtong Li to go on, please.
Okay, thank you for introducing me and thank you for inviting me to give the talk in the seminar. So today I'm going to talk about my research, which is a new fully mixed formulation for the Stokes-Biot model. So let's take a look at the overview. Since I know that the residents here might not just have a numerical background, so I'm going to give a little bit background for a finite element method and also mixed finite element method. And then I'll spend some time talking about my research is basically mixed finite element method. And the topic today would be for the Stokes-Biot model. I'll start with a brief introduction and then most likely focus on the fully mixed formulation. And finally, I'll show you guys some numerical results. Okay, so what is finite element method? It's actually a widely used method for solving differential equations numerically. So to illustrate this idea, let's start with a second order elliptic equation like this. So the model is as follows. We have a domain omega in, for example, 2D or 3-dimensional setup, and we would like to solve for P here. In fluid dynamic, we can consider P as has a meaning of pressure, which is a scalar. And now K is a conductivity tensor. It is a parameter, it's already known. And usually we assume it to be symmetric, positive, and definite. So the finite element method is not based on directly the PDE, but rather a variational formulation of the problem. So what we'll do is I'm going to omit introducing you the subless space. I'm thinking that you might have some knowledge on that. So just think that we are multiply our original equation by some test function in H01. And then performing integration by part, we're going to obtain this variational formulation. And our finite element method is just based on this variational formulation. And it actually could be shown that these two problems are actually equivalent if our P is sufficiently smooth. Now the question is, how do we solve this problem numerically? So this is still an infinite dimensional problem, right? So in order to do that, we need actually some discretization. The basic idea is that we're going to use the Galerkin method, which where we choose a finite dimensional subspace H SH0, which is a subspace of this H01, and then we look for our pH in this subspace, which is a solution of this discrete problem. Formally, you can just think about we are adding H everywhere, but in this process, we're actually reducing our infinity setup problem into a finite dimensional setup. So how are we going to deal with that? The finite element method is indeed just a general technique to build finite dimensional subspace in order to apply this Galerkin method to a variational formulation. And this technique is based on a few simple ideas. The fundamental one is that we partition our domain omega into a set of simple subdomains, just like this picture here. And we are calling it elements. And this is where the name finite element is coming from. And this element in 2D is usually triangles or quadrilaterals. And then we have the space of functions defined on omega is approximated by some simple functions defined on each subdomain with, of course, suitable matching conditions on the interfaces. So simple functions we usually use for here, I'm using polynomials, or we can also have functions obtained from polynomials by some change of variables. But let's just think about it to be polynomials. And roughly speaking, in this setup for the subspace, we are able to express our pH, the variable that we're interested, writing it in terms of a linear combination of the global basis function phi where phi is basically the basis functions for the space that we care about. Now, if remember that we are having this equation here, so if we are taking our WH, the test function, to be each basis function, then we are actually reducing our original problem into this problem, which is actually just solving a linear system AP equal to F. And A is already known from our setup. F is also known if you know the right-hand side. Now we only need to solve for P here. So that's kind of like the idea for the finite element method. And now I would like to point out that the model that I give, it could be used to describe a flow in porous media. And more generally, this is the Darcy's equation that we're having. But the trouble is that we only having pressure as a single variable. So usually what people care are also considering the Darcy velocity, which is a function of pressure. So one way you can do is you can try to approximate UH by using kind of like the same structure of equations. But this has some drawback because think about if we are trying to approximate pH by piecewise linear functions, then our UH will be, after taking gradient, right? It will be piecewise constant, which is discontinuous. So this is something that we do not want. And also when we are taking gradient in terms of error, when we're trying to compute that, we're gonna actually lose one order of convergence. And actually, naturally, we would expect velocity to have more regularity than pressure instead of like this way where our velocity have less regularity than pressure. And the other drawback is that people also want to have conservation mass. Roughly speaking, it's just that they want this equation to hold not only discretely, but also continuously, right? However, if you just say the model problem that we're dealing with, we do not say this equation explicitly, right? So mixed finite element method is really a special class of finite element method that approximates simultaneously several physical variables of interest. So roughly speaking, is that we are, instead of using the pressure formulation or pressure model, we are actually involving our velocity as another variable here. So this is going to be the model problem that will be based on to derive our formulation. And in this way, actually it has several nice properties in terms of actually this comparing with these two drawbacks. So for the continuous formulation, if we have appropriate space and then multiply with appropriate test function for both velocity U and pressure P, then we get this formulation here. And now if you want to discretize that, you just find appropriate subspace and then have this formulation formulate again, putting H on everything. Now the nice thing is that we have indeed mass conservation and actually even local mass conservation, because a subspace for L2 allows us to think about, for the test function, we can take it to be piecewise constant, then actually this divergence UH equal to F holds for each element. So that's a local mass conservation. And on the other hand, of course, since our UH is a variable, so we actually gonna obtain accurate Darcy velocity. And because of the space we choose, it will have continuous normal components in edges. So that's a rough introduction for the mixed finite element method. Now, my research is related to the study of mixed finite element method for a particular type of problem, which is fluid poroelastic structure interaction. I'm gonna do a little bit physical introduction here. So it's basically a problem that describes the interaction between a free fluid and a flow in deformable porous media. So think about we're dealing with two domains, and then the problem is actually a coupled problem. So this is a challenging multi-physics problem motivated by a wide range of applications. For example, we can do cleanup of groundwater flow in deformable aquifers, right? Then we have two parts. One is the groundwater flow, the free fluid, and the other part is the aquifer. The aquifer is an underground layer of water-bearing permeable rock or rock fractures. So they could be treated as a porous medium. Or in petroleum engineering, it could be used to, say, predict and control process which arise in gas and oil extraction from naturally or hydraulically fractured reservoirs. Again, you are going to have free fluid and also the porous medium. And also FPSI problem, which is the short for fluid poroelastic structure interaction, could also be used to model, say, blood vessel interactions. Then we are going to have the blood, right, inside and also the arterial wall around it. And also it could be helped to design the industry filters where you think of the gas as the free fluid, and then this filter is our porous medium. So we have a lot of applications motivated, and now let's take a look at how to actually have a mathematical setup for this problem. In this case, think about we're just having a connected domain that comprises of two non-overlapping regions. For example, for simplicity, you can consider two rectangular regions, right? So you have a fluid region and you have a poroelastic region, and it's connected by some interface gamma FP. And in this case, the free fluid, the free fluid is modeled by Stokes or Navier-Stokes equation. But for today's topic, I'm going to focus on the Stokes equation. The built system is used to describe this poroelastic media. So in the Stokes, the variable that we are caring about is this sigma f is the fluid stress. UF is the velocity, but also we are having the pressure inside. And also we are gonna complement with some boundary conditions. And for the built system, it's actually coupled, you can think about the coupled between Darcy and elasticity. I'm gonna talk about in more details later, but basically it's the volumetric deformation of the elastic porous matrix is complemented with this Darcy equation that we just talked about before, and it actually describes the average velocity of the fluid in the pores. And the two regions are coupled via some appropriate interface condition to complete this coupled system. And in particular, the conditions that we are imposing is going to be mass conservation, conservation of momentum, balance of normal stress, and the Beaver-Joseph-Sussman condition, which is actually a model of slip with friction conditions. And also, since we are doing a time-dependent problem here, so actually our system equations is also complemented by some initial condition. And in particular, we are start with the initial condition for P only, but then we are constructing compatible initial conditions for theoretical analysis. Now, I would like to focus on how do we actually derive the mixed formulation, or roughly speaking, fully mixed, because we are using mixed finite element method for all the three parts, the Darcy and elasticity coming from Biot, but also the Stokes part in the fluid region. So we already talked about this Darcy part. We're gonna use both velocity and pressure as two variables. And now for this elasticity part, we're gonna use a mixed elasticity formulation. But in terms of Biot, you can say that these are really just coupling between this Darcy and elasticity, right? So that's what we are dealing with here. But actually for the Biot system, the stress we care about are gonna be poroelastic stress instead of just the elastic stress, which also takes the consideration of the poroelasticity. And now we talk about the Darcy mixed formulation. So let's take a closer look at what the stress mixed formulation for elasticity would looks like. So in order to do that, we are introducing two more variables. One is the structure velocity US as the time derivative of the displacement. Actually, this is for simplicity of our theoretical analysis. And indeed, what the three variables for non-time differentiated one would be elasticity, the displacement, and also this rotation operator, which is a symmetric part of the gradient of the displacement. But since we are dealing with the structure velocity instead of displacement, so actually for the rotation part, we are having this structure rotation operator is also the time derivative of this rho p here. Now, the model problem that we're based on is going to be this one here. And when you are multiplying appropriate test function, you're able to get this weak formulation, which basically comes from the mixed elasticity formulation. And the nice thing here is similar to the mixed Darcy. We are going to have local momentum conservation, actually the local power elastic momentum conservation from this equation. And also, since we have our sigma p, the power elastic stress, as a variable, so it provides us accurate approximations, accurate stress approximations with continuous normal components across element edges or faces for this variable here. And for the Stokes part, we are doing something very similar. So the variable that we are caring about is also stress, velocity, and the vorticity is just having a similar role of the rotation operator in the elasticity equation. And actually, we're also introducing another, not a variable, but just some kind of like change for our fluid stress, which is the deviatoric part for stress, because when we are introducing this, we are actually able to eliminate the fluid pressure from our model problem. And finally, we can still recover the pressure from a post-processing procedure. But for the model problem, we only need to deal with 3 variables, which is stress, velocity, and this vorticity tensor, which is a scale symmetric part of the gradient of the fluid stress. And now here is the formulation that we are gonna based on to get into the coupled problem. So now let's take a look at what happens for the whole coupled problem. It's a little bit long, but basically I've already described you the basic components. You can observe that the first 3 are exactly coming from the mixed formulation for the Stokes part, and the middle 3 is exactly the mixed elasticity formulation, and the last 2 are going to be the mixed Darcy, the velocity pressure Darcy formulation. But actually some subtlety that I want to mention here is that we are also having 3 extra Lagrange multipliers, and the role that they are applying here is because one thing, so for example, for this one, this lambda is actually has a meaning of the pressure on the interface gamma FP. One reason that we are introducing this lambda, because if you are putting PP here, this term in terms of the Sobolev space setup is not going to be well defined. So we have to include another Lagrange multiplier. And the other reason is that we are going to use the Lagrange multiplier to impose the interface conditions weakly. So because of these 2 reasons, we are introducing the Lagrange multipliers. Lambda has a meaning of the trace of PP and also corresponds to 2 other mixed formulations. We are having theta has a meaning of the structure velocity on the interface, and this phi has a meaning of the fluid velocity on the interface. Again, without introducing them, the term would not be well defined, and we are not able to having the interface condition imposed appropriately. So this is the continuous formulation. And now think about if you are introducing appropriate subspace, then formally putting H on everything, you're going to get the discrete formulation. But because of the time, I'm going to omit all the theoretical analysis, but roughly give you a picture of what are we doing in the theoretical analysis. So as I said, since we are doing a time-dependent problem, actually the discretization procedure is on 2 steps. So we start with a continuous one. And then the next step we are going to do is we are going to only discretize with respect to the space instead of time. So we get the semi-discrete formulation. So it's just the time is still continuous, but the space variable are going to be discretized. Now, the last step, as you can imagine, we also discretize the time to get the fully discrete formulation. Now, for the continuous setup, what we care about is that in the formulation, do you have indeed a solution? that is the existence of solution. And if you have, is the solution unique, right? So that comprises of the well-posedness analysis. And another thing that we're caring about is that if you have the solution, will it be stable? It's really just say that is our solution able to be bounded by all the source terms and data for initial conditions such that like this. So this is some property that numerical guys are always caring about for the continuous one. Now for the semi-discrete one, we also want to know if we indeed have the well-posedness for our semi-discrete solution, and if we have, will it be stable, right? But one more thing we care about is about the error. So for example, you are having the variable u and you are approximate with say UH, right? Then we kind of like want to know the error in appropriate norms. Is it if you, since you are discretizing the space, if you are shrinking, say the mesh size using in the space, are you are able to get the appropriate rate of convergence that, that you expect? So that's basically the three parts that we are caring about for the semi-discrete case. Now for the fully discrete case, exactly the same procedure. But since we're usually, we are caring about more like the space instead of time. So for the fully discrete, the natural thing we're using is going to be the backward Euler. And actually all the theoretical analysis, the well-posedness, stability, and error analysis would carry on from the semi-discrete case. So in my paper, we are focusing on the continuous case and semi-discrete case, but for the fully discrete case, we really just presenting the final idea without giving specific details. So that's kind of like the theoretical part. Now for the last part, I want to talk about numerical experiment. That's always where we end up with for the numerical guy, right? So let's, I'll talk about two examples here. The first example is a convergence test, testing really whether our error is indeed converging with the rate of convergence as we expected. So for simplicity, we consider a two-dimensional test case. It's pretty simple. Is we are having two just this two units, right? And our coordinate system would be 0, 1, and 2, -1, 2, 1. And the upper half is going to be the Stokes region, and the lower half would be the power elastic structure. Of course, appropriate interface conditions will be enforced along this interface y equal to 0. And luckily, we have some analytic solutions here, and we're going to calculate the right-hand side and also the other solutions from this analytic solutions here. And also we complement our model with appropriate boundary conditions and initial data. So the total simulation time here is 0.01 second, and we take the time step to be 10 to the -3 seconds. Note that we are taking this time step to be sufficiently small because we do not want our time discretization error to affect our convergence rates. And now here is a table. So one thing that I didn't mention is that in our theoretical part, actually our error analysis does not restrict on the setup that we have to have matching mesh size for the Stokes and Biot. And as in this plot illustrate, you'll see that we're having smaller mesh size for Stokes than Biot. So this also says that our methods are able to actually handle with the non-matching grids. So in this table, we are also showing the results for non-matching grid, where we are setting the mesh size to be H Stokes to be only 5/8 of H Biot. Actually, you can choose some other ones, but this is just the one that we choose. And as you can see, all the variables that we are having are actually having basically order 1 convergence in their natural norms. And also remember in our formulation, I said that we eliminate the fluid pressure. And here the error actually we are obtained by a post-processing procedure and then compute the error. And similar thing is we are doing for the displacement. And nicely, we are also having the order 1 convergence. So although we do not have the variables explicitly in our result, but indeed they are converging as expected. And now for the Lagrange multipliers, since in this case, our Lagrange multiplier space are basically in H1 half norms. So they exhibit order of H3 half convergence is also expected when we are using a P1 element approximation. So that's for the convergence test. Now for the next example, I want to talk about irregular shaped fluid filled cavity example, which is motivated by modeling the flow through, say, vaggy or naturally fractured reservoirs. And here the domain is again a unit square, but it has a large fluid filled cavity. And indeed, the parameter here we choose are realistic for hydraulic fracturing. And I want to emphasize that we are having pretty small S0, which is a storativity, and pretty small permeability, and also relatively large lambda p and mu p, which are Lamé parameters. And actually, these parameters regimes are known to lead locking in modeling of the Biot system of power elasticity. So usually it would cause trouble. For example, your station would be unstable. But what we want to show is that our methods are indeed able to handle this kind of like computationally challenging problem. And we set the body force, external force, and source and initial condition to be 0. And you can see that the flow is basically driven from left to right via a pressure drop of 1 kilopascal. So we are having 1001 on the left and 1000 on the right. So you can imagine that our fluid is flowing from left to right. And the time we have is 10 seconds with delta t to be 0.05 seconds. So now here is the results we get. So in the top plot, we are presenting the first one is the Darcy pressure with the arrows to be the velocity vector. And the second one would be the displacement magnitude together with its vector. And the last part is the first row of our power elastic stress magnitude with also its vector. Everything are at the final time step. So since our pressure variation, remember, it's just 1 compared with its value 1000. So for visualization purpose, actually this PP here, what we are presenting is actually indeed PP subtracting the reference value 1000. And now we note that actually the Darcy velocity is largest in the region between the left inflow boundary and the cavity. And also the displacement is largest around, say, the cavity. And it's understandable because we are having large fluid velocity within the cavity. And also remember on the interface, we are having the slip with friction interface conditions. Now for the power elastic stress, it exhibits some singularities near some tip of the sharp tips of our cavity here. Now for the cavity part, it's the fluid region, right? So we present the fluid pressure still PF minus 1000 and with the velocity vector, and also the velocity magnitude with its vector. And finally, the first row of our fluid stress with its vector. So now it's clearly that we can see a channel-like flow profile along this cavity. And the largest velocity occurs on the central path away from the cavity walls. The fluid pressure is decreasing as they go from left to right, right? And also consistent with the power elastic stress, our fluid stress near tips on the left side of this cavity is relatively larger. And again, I want to emphasize one more time that although we are having our locking regime because of the parameter we chose, but our computed solution is still stable. And this example illustrates indeed the ability of our method to handle computationally challenging problems with also physically realistic parameters in power elastic locking regimes. Okay, so that's everything I want to talk about. If you have any questions, you're welcome to ask, and thank you for your attention. That's it.
Thank you, Tongtong, for your talk.
Thanks.